Okay, so thank you for the introduction. So one of the original goals of microlensing surveys of the galactic bulge were measurements of the microlensing optical depth. But for many years, these measurements suffered from very small statistics, and I'm proud to say this is about to change with my new analysis of OGL4 data. So as you probably know, the microlensing optical depth tell you something about the distribution of mass along the line of sight. Similarly, the microlensing event rate gives information about the distribution of matter, but also on velocities of sources and lenses. So if you measure optical depths and event rates toward many sight lines in the direction of the bulge, you can constrain models of the structure of the central regions of the Milky Way really precisely. But such measurements were conducted over 20 years ago, already in the 90s. But practically all of these measurements, with one exception, were based on small statistics. The only exception is, of course, the analysis of MOA2 data by Takasumi, who analyzed almost 500 microlensing events in the bulge, but in some regions, especially very far from the galactic center, the statistics is very poor. So I analyzed new observations from OGL4. As Janek mentioned, we are looking for microlensing events in over 120 fields toward the galactic center. This is an area of about 160 square degrees, an order of magnitude like 4 times larger than in the previous analysis. We observed the galactic bulge with varying cadence, starting from observations every 20 or 60 minutes. Some fields are observed every 2 or 3 days, but this is still sufficient to find microlenses there. I analyzed the data from 8 years of OGL from 2010 through 2017. I analyzed over 400 million stars in our databases. This resulted in the discovery of about 8,000 microlensing events. Some of these were already published. Some of them are new discoveries. But as far as I know, this is the largest homogeneous sample of microlensing events ever analyzed. So from the observational point of view, if you want to measure optical depths and event rates, you have to measure two quantities. First of all, you have to find your microlensing events, you have to measure their time scales, and you have to assess the detection efficiency of your experiment. The second problem are stars. You have to count the number of monitored stars. And I think of those two, the second problem is more complicated. So of course, right now with such large sample of microlensing events, what actually limits us is not small statistics, but the accuracy of star counts. Of course, the most robust way to count stars is to use very deep HST Hubble Space Telescope observations. But such observations exist for a couple of sight lines toward the galactic center, but of course we cannot afford to observe the entire bulge with HST. So we have to use some other approach. We tried image level simulations. So we injected artificial stars to our images. We created artificial reference images, and we tried to recover the fraction of stars that we can detect. So for example, in really dense fields like this one, we are able to detect stars down to 18th magnitude. On the other hand, in some empty fields like that one, we can find stars down to 20th magnitude. So we used our simulations to correct our observed luminosity functions and to count stars. We compared these results with HST, and the results are quite nice. So the accuracy is typically of about 5%, In some very rare cases, the difference is at 10% level, but it's still quite, it is still quite small. So this is the map of star counts. In our fields, of course, we cannot detect many stars here close to the galactic center, galactic plane where the extinction is really high. The second thing is that you have to find microlensing events, and the selection criteria for microlensing events were pretty straightforward. I don't want to talk about that a lot. We also conducted catalog level simulations in which we injected artificial microlensing events into on top of light curves in our databases. So this allowed us to estimate the detection efficiency, and as you can see, we can still find events with timescales of about 1 and 2 days. Okay, so this is the distribution of timescales for our sample of 5,800 microlensing events. Timescales are measured quite precisely with typical accuracy of between 10 and 20%. This is the same histogram, but it is corrected for detection efficiency. And we see what we have seen before, so nice parallel tails with slopes +3, -3. This is what you expect from theory. We do not see any excess of events here. As I said, we are still sensitive to events with timescales of about 1 and 2 days. So this is the map of mean timescales. The closer to the galactic center, the shorter timescales we observe. And this is actually consistent with what you expect from theory. This is also consistent with previous results by Łukasz Wyrzykowski. This is my favorite map, which shows the microlensing event rate in our fields, which is based on a sample of events that is a factor of 15 larger than previously. So what is really nice is that the contours of the constant density, the constant event rate, have this hexagonal shape, and this is what you actually expect from galactic models, which were created already in the 90s. So after 20 years, after these simple models, finally we can see this pattern. This is microlensing optical depth. It's not as nice as the previous map. It's more grainy, and this is because microlensing optical depth depends on timescales of events. So if you have only one really long event, it makes the entire depth much larger. I also compared these results with the simple Besançon model of our galaxy, and the results are pretty consistent. And as Janek mentioned at the very beginning of the conference, we are also observing the galactic plane, entire galactic plane that is visible from Las Campanas, and we do find microlenses there. We can find microlensing events as far as in the anticenter of the Milky Way. So far we found about 200 microlensing events there, but this sample is large enough to have some glimpse what's going on there. So for example, we can see an excess of events below the galactic plane, and we think that this excess comes from a warp of the galactic disk. This is the similar situation as seen in the classical fields, which also lie below the galactic plane. Yeah, so that's all. I just wanted to put this picture again. Thank you.
So I had a question on, for these event rate maps, what conditions do you set on the source stars? Do you have a magnitude limit? Or?
Yes, I have magnitude limit of 21.
Okay, and are you, your sensitivity presumably to magnitude 21 depends on crowding? Is it?
So I think it's included in simulations. So as I said, we did catalog level simulations, but For the previous paper on free-floating planets, we used image-level simulations. We actually compared the results, and the efficiencies, detection efficiencies are very similar for both types of simulations. So, yeah.
Subo.
Oh, sorry, my thing turned green. Okay, so I was wondering for your galactic plane microlensing events, given that the cadence isn't as high as it is in the bulge, did you have a figure for the distribution of the time scale of those events?
Yes, I have, but I can show you. I can show it to you later. I don't have it in the talk.
Okay.
Yes, but generally because our cadence is lower, we are more sensitive to longer events. But on the other hand, galactic models predict that the timescales of events in the galactic plane are longer, and this is because you are observing this cleansing, so they should be longer.
Do you take into binaries in your
No,
event rate?
no, I don't.
You just excluded binary events?
Yes, so they are excluded by selection criteria. I just pick point source, point length events. So, but I'm not sure how to include this.
Then the concept for about 10%
Yes.
of all events.
Question, Matthew.
Yeah, what's the effective resolution of the maps, and do you have event rate per source maps as well?
So the resolution is about for this one is 10 arc minutes. And what is the second question?
Do you have event rate per source? So they should be a lot smoother rather than event rate.
No, not yet.
Okay, those would be good.
Quick question, Yoshi.
You had a plot showing both the SUMI event rate and your event rate. Do you find any differences, or is it just different resolution?
In the central regions, there are not many differences, but the previous map is based on small number of statistics, especially very far from the galactic center. So because we have much more microlensing events there, our map is more accurate in that region.
Right, let's thank Przemek again. So next speaker will be Samson Johnson from Ohio State University about the microlensing WFIRST survey and prediction about.
Can you guys hear me all right?
Stand by one second. We're working on that screen right now.
Oh, no worries. Awesome. Yeah, so my name is Samson Johnson. I'm a graduate student at The Ohio State University, and I've been working with Matthew Penny on the simulations he wrote to design the microlensing survey for WFIRST. And sort of the first thing I've been doing with that is estimating WFIRST's ability to, or what WFIRST can tell us about free-floating planets. For those of you, well, no, as we already know what WFIRST is, it's an infrared space telescope that's going to be launched mid to late 2020s. But just for the science case of WFIRST here, if we look at the mass of exoplanets versus their semi-major axes, we can see the black points are those essentially detected from the ground, and red is the contribution from Kepler. From this, we are starting to get a much clearer picture of what the inner portions of stellar systems looks like. But we can see that there is a large region of parameter space beyond that we don't know much about. And this is interesting, first off, because if we look at the pictures, those are our solar system planets, obviously. But it's also where a lot of planet formation is thought to be occurring, beyond the ice line, where volatiles can condense, and you can start forming potentially giant planets. Planet formation might also be a very dynamically violent process, in that planets migrate and also could be ejected, and this could be a possible source of free-floating planets. Now, microlensing is probably the best way to detect planets in this region, and also isolated low-mass lenses, such as free-floating planets, and that's exactly what WFIRST is going to do. So here in this plot from Penny et al. 2018, the blue points represent a simulated yield of planets that WFIRST would be able to detect. And as you can see, it complements Kepler extremely nicely, and that it's a comparable number of planets in a much different, with much larger semi-major axes. So this, the picture that we gain from getting both would be to start getting a full characterization of what stellar systems look like. Now, WFIRST is going to be able to find these planets because of how the survey is designed. The main points I want to get across of the current survey design is that it's got a fairly, it has a wide field of view, about that 100 times that of Hubble with similar resolution, and it'll have about a 2 square degree survey footprint in total that's going to sit just towards the galactic bulge and just below it, where we're balancing extinction, event rate, and all those things. There'll be 6 72-day seasons, which will be clustered at the beginning and end of the mission lifetime, so separated about 4 or 5 years, which will help with measurements of lens source separations with that long baseline. One of the most important parts is the cadence, which we sort of talked about earlier, but it's 15 minutes in a 1 to 2 micron bandpass. This very high cadence will allow us to characterize short timescale perturbations as well as short timescale events. And there also will have some potential for measuring colors in a much higher, in a lower cadence sort of Z band, but that's still being figured out. In total, there will be greater than 30 or 20,000 microlensing events detected by WFIRST, yielding about 1,400 planets. But this is the current survey design, and it was a product of the simulations that Matthew Penny details in his 2018 paper that was recently accepted. And the simulations are called goals. And so sort of to give an update on those, there's just the quick update on those that's, as I said, much detailed, much better in the paper, is that the source count rates are being normalized. And the source count rates and the event rates per source are as up to date as possible. We should be integrating things from like the OGLE. That would be interesting, what we just saw. But another major point is that WFIRST is now going to be orbiting L2 rather than a geosynchronous orbit, which could enable measurements of parallax, or microlens parallaxes. Another thing that occurred between the last survey design iteration and the most recent one is that there's now more realistic slew times, slew and settle times for repointing the telescope. These effectively doubled and reduced our fields from 10 to 7, but in the future there is a possibility for newer reaction wheels that could decrease those slew times again, and we can try and account for those by using the simulations and optimizing it into the future. Yeah, so all that said, WFIRST is going to be able to give us a much clearer picture of exoplanet demographics in the far reaches of stellar systems and beyond. So sort of transitioning now into the free-floating planet work that I've been doing, just as motivation, this is a video from Sean Raymond et al. In 2012, where we have a number of small bodies in the inner and outer portions of this system, and then 3 large bodies. And we'll see that shortly after formation, about 40 million years, it'll quickly dive into chaos. So we'll lose all of the smaller bodies, or essentially all the smaller bodies, and even one of the large ones. Planetary, we could expect that it's theorized that there is a population of free-floating planets. So this could be a potentially good test of planet formation theories. And there's also evidence for this as well. It's tentative, but we, as reported in Rose et al. 2017, there was an excess of short timescale events, which would be consistent with a population of free-floating planets within the galaxy. Now, if we look at one of the recent candidates, or also there's another question about differentiating widely bound planets from those that are truly free-floating. So if you have an extremely, far outside the Einstein ring of the host, you may not see any signal from the host mass in the microlensing event. So it could be some confusion there, but there are ways around that we can talk about later, that we've been thinking about. I wonder if that changed the slide. We'll see where we end up. Yeah, okay, so if we compare, so we've seen this plot a few times now of a recent free-floating planet candidate that showed strong finite source effects and a very long, a few-day time scale. That's on the left, and then on the right is a simulated WFIRST free-floating planet candidate on the same baseline of about 10 days. And the source and the events are different magnitudes, but we can see the difference in a second. Or is it? Oh, it's not over there. We'll see that the event timescale that we're able to detect is actually much shorter. It's going to be about 2/10 of a day. So it can WFirst is going to get down to much shorter time scales and be able to.
Stand by 1 second. We're working
yeah.
on the image.
I can just, should I just hold on, or yeah, I'll just hold. So you guys even paused the clock. Awesome. All right. So yeah, if we just to get back, so we're looking at an actual candidate versus real simulated or real fake data. On the left, there should be comparable masses. This one was consistent with a few Earth mass lens, and same with this on the right. But if we zoom in on the event, we just saw that we were still able to characterize finite source effects with our high cadence, and could see that characteristic in the magnification, the characteristic shape. Now, if we look quickly at the detection efficiency, this is just showing it's very short, but if we look at the detection efficiency for WFirst as a function of timescale events, here the solid black line is the intra-season, so during a 72-day season, how many events we recover from those injected. We can see that it stays out to about 80 or 90% down to a tenth of a day. And then for the entire survey, looking at all 6 seasons combined, we still continue that trend where it's essentially flat, but around like 10 to 15%. Those vertical lines were the timescale or typical timescales for, or potential typical timescales for the masses indicated. I'll be, they're here too. Okay. So here, so as I said, vertical bars are typical timescales. And so just to talk about finite source effects again, just here I have the gray circle shows, if we scaled the source to be the size of the gray circle, the some typical Einstein ring sizes would be here in the red, orange, green, blue, and purple. And then we can see what kind of effects for the exact same event essentially, or for the exact same event except for changing the mass of the lens, we can see it has pretty obvious effects on the magnification curves and getting to the point where once your Einstein ring size drops below the size of the source, you saturate in magnification, it becomes sort of a top hat. And so here, once again, rho star is just the normalized size of the source to that of the Einstein ring, and that happens when rho star is getting around 1. And so sort of a benchmark that we can look at here in this cumulative distribution is that when you divide rho star by the impact parameter u naught, around 1, then we'll get some occultation of the source and potentially start seeing finite source effects. So I'm going to put this rough boundary here of what we'll say is finite source effects. But if we assume a fairly simple mass distribution, that there's one lens per, like for the 50 Jupiter mass case, we assume there's one of those per star in the Milky Way. We don't end up finding a large number of them, but very few would exhibit finite source effects. As we drop down in mass to about a tenth of an Earth mass, we would find very few, but almost all of them would exhibit finite source effects, sort of facilitating the measurements of masses. And then we also talked about parallaxes a little bit. Because WFirst is now at L2, there is some subset of events that we will be able to measure parallaxes for. Here in an example light curve from an LST white paper by David Bennett et al., we can see that there is some offset from viewing the event from different locations. And that would also, once again, needed for mass measurements. So looking into the future, what I'll be working on as Matthew transitions out of this, I'll be transitioning in and working on the simulations, updating those to make them as realistic as possible. We're looking at using a new galactic model, which should be more accurate, hopefully, as well as we're looking to compare our simulated event rates to those measured by you, Kurt, and maybe potentially the ones from Ogle as well. That would be very interesting. And also response to say, like, if we got new reaction wheels, adapting the survey design to best utilize the system architecture or the mission architecture. Going to be continuing on with the free-floating planet and characterizing what WFirst can do there. And then as well as another sort of farther future, I'm really interested in looking into what how WFirst can constrain statistics on Eta Earth. And with that, I'd be happy to take any questions.
Question for Samson. Yeah.
Could you say a bit more about distinguishing between wide separation planets and free floaters?
Yeah. So the obvious thing is looking for light from the lens. Just looking for light from the lens once some time has passed, and trying to see if anything is separating there. Another thing is you can sort of look at statistically how many detections you would expect from wide but still bound planets. And then if you see some excess in events, well, I guess we don't have a good distribution, or you don't have an understanding. But once we start getting statistics, we can start to compare those and see if we see some excess of events, I guess. Does that make sense? Okay.
So I had a couple of comments. First of all, the WFIRST has already decided to go to the higher torque reaction wheels.
Oh, it has? Okay.
But they haven't worked through all the power requirements to guarantee that we have the power to use them yet.
Okay.
And then the LSST white paper you referred to was not Bennett et al. It was Street et al.
It was Street et al. Oh,
and
my mistake.
She did a lot more work on it than I did, that's for sure. And
that's my fault. Sorry.
Simulations are from Matthew Penny that we used for that.
Yes. Okay.
The other David.
Yes, concerning the free-floating planet simulations, I'm just wondering about the definition. Let's say there's a solar system analog. Would Neptune or hypothetically Planet 9 count as free-floating planets?
That's the distinguishing between those that are bound and then those that are actually isolated planets. I guess trying to tease out whether they are bound or not is still up in the air. Is that what you're asking, or what do you mean?
Yeah.
Okay,
Because I think at some point the planet's so far away that you only see one lens potentially, but I'm not quite sure how far away that typically is.
I mean, so you're most sensitive around Einstein ring. So getting beyond let's say 10 to 15 AU, that's when you really start dropping off in sensitivity, I would think. But that's just something like that. Yeah.
Okay.
Quick question, Andy. Yeah.
So I think that if you resolve out your sources and confidently, and so you think you don't have any blended light, then you can detect these finite source effects out to about twice the source size. You don't have to intersect. You don't have to transit the source. You can go to two source sizes.
Okay, gotcha.
To detect it. So I think this should somehow be put into these simulations.
Okay. Yeah. This, as I said, was just a quick benchmark.
All right, let's take Samson again. Next speaker is Rachel Rickerson from IPAC, and she's going to speak about the community data product of WFIRST at IPAC.
Thanks, Etienne. So I'm Rachel Aikison. I work at IPAC at Caltech, and we're one of the science centers for the WFIRST project. And so I want to give you a little overview of how the data processing is going to work for WFIRST and describe the data products, and then point out a couple of the challenges as I see it from our end, not as the science team, but as the science center. Okay, so first off, WFIRST is a very distributed project. And like all NASA projects, has a plethora of acronyms. And so I will try to define them, but if I get a little too NASA speak, feel free to stop me and ask for clarification. So as far as the microlensing is concerned, there's actually three important groups in getting the data process. The first is the SOC, the Science Operations Center, which is at Space Telescope Science Institute. The second is the SSC, the Science Support Center at IPAC. That's the group that I lead. Don't ask me who came up with these names. It was not me. And then there's the Science Investigation Team, which is called the SIT. Again, everything has to have an acronym. The current PI of that is Scott. But it's also important to recognize that the way NASA missions work, there's often two phases of science teams. Right now, we're in what's called the formulation phase. And so that was a selection a few years ago for a 5-year science team. all the science teams at WFIRST are going to get recompeted probably in 2021. And it's that second science team that will be involved in the work that I'm going to talk about. Okay, so now between these three groups, what happens? So the SOC processes all WFI data, including microlensing, for the initial calibration. Then it's handed over to IPAC, to the SSC, and we're going to do all the microlensing specific calibrations, run the pipeline to do source photometry, catalog generation, and completeness and reliability. Then the SIT has a very key role in that they're going to be providing the pipeline algorithms, but they actually also have to run part of the pipeline themselves. They're going to develop and run the part of the pipeline that identifies and characterizes the microlensing events. And then at the end, they'll be calculating the occurrence rates. And so this is a little flow chart attempting at a very high level to sort of what I've just said. So the SIT's currently working on a much more detailed version of this that goes in the details of these different boxes. So don't get too hung up on the exact contents of these, but this sort of shows the flow and also a little bit of the complication in that by having so many groups involved, that does add some challenge to it. So in purple on the left here, we have Space Telescope. They're going to run all the microlensing through the same WFI pipeline that all WFI data gets done through. But at IPAC, we're going to take the data out at the level of the calibrated exposures, so no time averaging, obviously. And that's when the microlensing specific pipeline starts. So there'll be extracted photometry, catalog generation, and we're going to automatically generate a catalog of all variable sources. But again, to actually identify the microlensing events, that gets passed along to the SIT. That information gets passed back to us. We do some more products, and then the pipeline completeness and reliability. And then finally, at the bottom, one of the big goals of WFIRST microlensing is these planet occurrence rates.
Where's it getting passed back to you in this chart?
In this chart, it's the catalogs and the microlensing events actually have to get passed back to us so we can run things on completeness and reliability. Okay, so just to know where you are in all this, I think Samson mentioned that the current launch date is towards the end of 2025. And so what we're doing right now is we're working with the SIT to define the pipeline steps in much more detail here, the preliminary algorithms and the contents of the data products. This is leading to what NASA calls a preliminary design review in about 1.5 years. But what I kind of want to emphasize here is that the major effort to actually write the pipeline code doesn't start till the review after that, which is called the critical design review. So this is important, I think, for this venue because, as you'll see, I'll raise some questions at the end about where I think the challenges are. We do still have time to identify ways to address these challenges. I do not have a staff of 10 developers sitting in Pasadena right now waiting for answers to start writing code. And so hopefully some of the stuff that's going to come out in the hack session can be fed into things that we can take advantage of. Okay, so I don't think I need to go through this because Samson covered this very well. So let me actually spend a few minutes talking about the data products. So I think these are things that you'll expect, like the calibrated images. There'll be a source catalog for all sources in the survey field and photometry for all of those. Things like position and Scott's favorite skew and kurtosis, or what is it you always call them? Moments. The moment curves. And so one of the things I want to emphasize is by the end of the survey, there should be roughly 40,000 images of each of these fields and photometry for over 100 million sources with precision of better than 1% down to a little fainter than 21. And so this is really going to be a very unique data set for all sorts of science. Then there'll be another catalog just for the variable sources, and that's what the SIT can use to look for the microlensing event catalog that they'll be generated. The other thing that's unique about the microlensing survey is because it's going to sit on these same fields for so long, this is by far the deepest images that any of the WFIRST surveys are going to do. There are other cosmology-related surveys that you probably know about, but those are much wider surveys. And so the calibration products derived from this data are likely to be the best available for WFirst. And we're working to figure out how those actually get fed back into the main pipeline so everyone gets the best calibration possible. Here's just sort of a list of things that the team is worried about. And then there'll be products that you can only generate when you get to the end of a season, that is the 60 or 70 days of the galactic bulge, or even at the end of the survey. So super sampled images of the entire field, relative source lens proper motion, and parallax. Okay, so one thing I really want to stress is that there is no proprietary period for any WFirst data, not just the microlensing I'm talking about, but any of the mission. And so currently our goal is to have the basic data products, sort of the calibrated images and the photometry, available to everyone in the archive within 72 hours of being taken. And I will point out that actually most of that time is not for processing. Most of that time is getting the data down from the spacecraft and transferring it around the ground system. And so hopefully that will take less time than the 48 hours that is currently allocated. And so there's a real possibility that the 72, this is the requirement. We absolutely have to meet this or we get in trouble. So I'm hoping this is really closer to 48 hours. The higher level products like the catalogs and stuff that take more processing, those will come out either at the end of the season or the end of the survey, depending on when exactly they're generated. Okay, so a few challenges. So the data rate is something that the project is actually very concerned with because when it's launched, WFirst will have the highest data rate ever brought back from L2. And so this is a bit of a stressor for the sort of NASA ecosystem of bringing data back from L2. But if you actually just look from an astronomy perspective, so the max rate is 11 terabytes per day. That is totally capped by what the spacecraft and the ground system can do, not by what the scientists would like. So it could go up if they find a way to bring more data back. The plan is to process that daily, but at IPAC, we already handle a set of photometry from Palomar that's actually a higher data rate than that. LSST will be even much higher. And so from a purely processing point of view, as long as we allocate enough resources, this really isn't a problem on our side. It's much more a problem on the ground system and the just communicating between L2 and the ground. Okay, so moving on to microlensing specific things, so event identification and characterization. So as I said, the data products include catalogs of variable events and microlensing events. So there's a lot of light curves to look through, 100 million, and a lot of microlensing events. So those are larger numbers than the current surveys. And so these, if we're going to keep up with this 72 hours for the light curves, we need to have new methods to sort of keep up. So there's been some examples in other areas like Kepler, but I think this is one of the big roles of the data challenges. Rachel's going to talk about this on Wednesday, and this is hopefully one of the goals of the hack session. We're also going to hear a little bit about machine learning from Jeff and Dan. I feel like this is an area where there's a lot to learn. I will say when I Googled machine learning and XKCD, I had like 30 things to choose from. So, this is clearly a very hot topic right now, but, I hope we can find something that is really relevant and actually helps us out instead of just sort of, ticks off some buzzword. And then on the pipeline characterization, so one of the very high-level science requirements of WFirst is to estimate eta sub Earth. That is the frequency of Earth-like planets orbiting solar-like stars, and here's all the numbers if you want to know exactly how it's written out. And so to really do this, we obviously have to understand the efficiency and detection efficiency and false positive rate, as we heard earlier in the session. And so to really do that within the resources allocated, everything is going to have to be automated. And one of my concerns is we may not have enough resources to do all the injection at the image level. We may have to do the injection of the false sources at, say, the light curve level. And so, one of the things we need to understand is what biases might that introduce? Do we do a limited number of testing at the image level? Okay, and then finally, We're going to hear a few talks here about other science that this survey will enable. But the way the resources are currently allocated, there'll be the data products released to everyone that I listed, but the microlensing pipeline can only focus on microlensing. And so, one of my concerns as a member of the science community is how do we figure out how to do this within the rules of how we're allowed to spend our resources that actually let the community do as much other science as possible from the catalogs and the data products that are produced. And how do we support them in a way that is allowed without sort of appearing to do non-microlensing work. Okay, so in summary, there's going to be this amazing survey of 2 square degrees in the galactic bulge, and that's all going to be available to the entire community. That'll allow a lot of microlensing science, which you've heard about, but many other science areas. But there are some challenges that we need to really try to address in the next couple of years before we really get into the period of writing this pipeline. Thank you.
Question for Rachel. Michael?
Hi, Rachel. For the microlensing survey, is there a subpixel dithering strategy?
Scott, who is in charge of that right now? Or do you want to take that one?
So we haven't completely decided on the dithering strategy yet.
Will there be one?
What?
Will there be a strategy?
Yes, there will be. And the conflict is between, well, there's a tension between the microlensing survey that would like to do sort of relatively small dithers to map out the sensitivity of the pixels that the stars are landing on, but the weak lensing survey would rather us do wider dithers so that we can characterize the quote-unquote blank sky between our bright stars. So likely we're going to do some hybrid dithering strategy where some fraction of our dithers are small and then some fraction are larger than that.
Yeah, I mean, you must emphasize to these people that you're not going to get good difference imaging photometry if you don't dither properly.
Right, and that's understood.
Right, but as I said, this is the opportunity for the mission as a whole to get really good calibration. So that's the tension that Scott was talking about.
And just to add, there's a pointing repeatability issue in the dithering as well. So if you want to go back to an exact point in a pixel, that will cost you in terms of overheads.
Yeah, so actually better not to. Right. So I would. In some sense, we have to dither because it would take us so long to settle to the point where it's not like Kepler where we're pointing to a fraction of a pixel forever, right? So there's going to be a dither whether we like it or not. The question is, how big is that dither going to be?
Okay, quick question, Andy.
So among all the data that's being downloaded, by far the most interesting is existing microlensing events, which is only 1 gigabyte a day to get patches. So is it possible to get those down faster?
In our current design of the ground system, no. That might be something that could, so I will say one of the things that was mentioned earlier is that some of the international partners are looking at contributing ground stations, and that would bring some of those timescales down.
It's just a matter of organizing.
Yeah, so it's part of it is how much they're willing to redo the software on the spacecraft to do that. But the other factor stretching out that 72 hours is how much ground station contact time they have and what are the gaps between the ground stations. And so there's also the chance that all the data could come down more quickly if the international partner ground stations all get finalized.
All right, thanks, Rachel, again. And our next speaker is Somaya Kashbshak and she's gonna speak about a simple approach for modeling for W1st.
Hi, my name is Somaya Khakbash, and I'm a graduate student at Lehigh University. I've been collaborating with Matthew Penny at Ohio State University and my advisor, Joshua Pepper. We have been working on this project to create a method that can, a fast method that can give us an estimation of planetary parameters of a large set of planetary microlensing light curves. In this talk, I will first give you an introduction of why we think this method is important and where the initial idea of this method comes from. And then I will discuss our method, and then I will show you some examples of successful and unsuccessful cases, and then I will show you an overall plot showing the results of this method. Okay, so what we know is that the current methods to analyze each planetary microlensing light curve is challenging and time-consuming. For one reason, it's because the features in the light curves are not directly connected to the physical features of the event, and also there are higher-order effects and degeneracies that make this problem more complicated. In the era of large surveys, we think that the fast technique to find an estimation of the planetary parameters that can work on like a larger set of light curves would be necessary. So the idea was first suggested by Godin Good 1997 paper that suggests that we can look at the features in the light curve and we can parameterize the features, and from those we can find the planetary parameters S and Q. In this method, what we do is that we feed a single lens model plus a Gaussian curve to thousands of WFIRST simulated microlensing light curves. And from those, we get the 6 parameters, 3 of them describing the primary events and 3 of them describing the planetary event. And from these parameters, we, using the first order equations, we find the planetary parameters S and Q. And then we compare them with the true parameters of the system that we already have from the simulations. Here, there's an example of a successful fit in our set of light curves. You can see that the planetary perturbation has been well described by the Gaussian curve, and we have been able to estimate the parameters, and they're very close to the true parameters. If you look at the table of the values, you can see that the primary parameters and the planetary parameters are well estimated. And also, if you look at the residuals, the black residual is with respect to the single lens model where you can see the perturbation, and the red residual shows is the residual with respect to the single lens plus the Gaussian model, and the perturbation has been covered in that model. Here you see an example, another example of a successful fit for a perturbation in a minor image. And again, we see that the this method has been able to describe this type of perturbation as well. And the fitted parameters are very close to the true parameters. Okay, so here I'm going to show you a couple of examples of unsuccessful fits. We try to avoid to call them failures because we know that our algorithm is not designed to describe these kinds of events. One of these cases is a case where we have multiple caustic crossings, and well, we have more than one feature in the light curve, and this method is not able to describe the planetary perturbation well. Another case is where the perturbation is not large enough for the algorithm to detect it. And even though we use like a smoothing algorithms to get rid of the noise, for some of the cases, the algorithm could not still find the perturbation because it was just too small for it. And so instead, it just uses a set of noisy points as a detection. But the delta chi-squared of the two fits will be too small, and then we can see that there hasn't been an improvement. Another case is for the events with central caustic perturbations. we already knew that this algorithm will not work well for these kinds of events, because for this method, we're assuming that the projected separation S is between the primary lens and the planetary caustic, and therefore, for these kinds of events, the algorithm thinks that the planetary caustic is very close to the primary lens, and then assumes that the projected separation is very close to 1. So here is an overall plot for the parameters mass ratio and projected separation in units of log space. On the right-hand side, you can see the plot of the fitted projected separation versus the true projected separation. What we can see is that for most of the events, we can estimate the projected separation very well with a very low scatter. There are 2 features seen in this plot, and so one of them is a set of light curves that have estimated projected separations close to 1. That we have tried to eliminate them from this plot, and those are the central caustic perturbations that we didn't expect to get good results for them. And there's also another feature in this plot, which is the y equals minus x line here, that for these cases, the results are not wrong. It's just that the algorithm wasn't able to detect if these cases are like minor image perturbations or major image perturbations. So we assumed, for these cases, we assumed that with another set of like simple analysis, we can just fix that. So we manually fix this for this plot to see how that improves the scatter in the plot, and I will show the modification on the next slide. On the left-hand side, you can see the same plot for the mass ratios. You can see that, well, it's not as well as the projected separation, but we can see that we can estimate the mass ratio within 1 order of magnitude for most of the cases. And if you look at the black bars, those are the mean medians of the results, and it shows like the trend of the results here, and we can say that we have better results for the intermediate mass ratios. And this is the projected separation plot with the modification for the degeneracy in the S results. Another thing that we had anticipated from the beginning was that we were thinking that we will probably get better results for the systems with lower mass ratios. So we have plotted the projected separation plots for the different ranges of mass ratios, and we can see that for much lower mass ratio systems, we have much better results for estimating the projected separation. And as we go to the larger mass ratios, we get a larger value for the scatter. So what we can say is that this method works really well for the projected separations, especially for low mass ratio systems. And we can estimate the mass ratios of these systems within 1 order of magnitude for most of the events, and even better for systems with intermediate mass ratios. We believe that when there's like a large set of light curves, we can use this method to get an estimations of the parameters and the events, and choose the events that we want to first do a fuller analysis on them. And we also think that the results of this algorithm can be used as initial guess parameters for later full analysis of each system. And we also have this idea that the results of this algorithm might be useful to feed into machine learning algorithms and for classifying the microlensing events. Thank you so much.
Question for Sumaya. Andy?
So problem we found with real events is that see something that looks like a naive, perturbation, like you've talked about, but is actually fit pretty well, with some alpha diagonal because it's off peak, but it's actually fit pretty well by a binary with large mass ratio, but not planetary, and an alpha going to zero. Just some caustic looks like this, and it's running across and hits one of the caustic features and kind of looks like hitting the caustic of binary. So I wondered if you ran into things like this or tested for them.
Well, not specifically. Yep.
So did you try, universal fitting for some of the things that you detected, and you said you did correctly and that they possibly fit completely other geometries?
Yes, that's what we did.
You never found this?
Jennifer?
Since you said you found this S degeneracy, the close wide degeneracy, does your algorithm report just one value, which might be wrong, or does it capture both possible values?
So it can capture both possible values, but the like our initial setup was just that it reports two values, but what it does is actually checks like both like a minor image perturbation possibility and a major image possibility.
Yoshi?
Did you try to use it just as an anomaly detector, just to see what's the fraction of anomalies that you detected, even if you didn't get the correct parameters? And the second question, did you try another basis function, not just a Gaussian on top of a point source event, but something that can mimic two caustic crossing or something like that?
Yeah, so for the first question, no, we didn't use this as like an anomaly detection. All of our light curves were planetary microlensing light curves. So we already knew that there are events there. But so for cases where the perturbations were not large enough for the algorithm to detect it, those were the cases that we were thinking that like they have not been detected. And for the second question, no, we have only used this Gaussian function so far.
Another quick question. Django?
Comment, okay? Your analytic expression, very simple expression, works only for the case, the source trajectory passes through the planetary caustic.
Yes.
And among the events, nearly 70 to 80% of planetary events detected are caused by central caustic or regional caustic.
Yes, that's right.
That means nearly more than half of majority of events does not follow your analytic expression.
Yeah, this will not work for the central caustic perturbations.
What I'm saying is a majority of them.
That's now though.
Yeah.
W first will have.
So W first will have many more events that are planetary caustic events because it's continuous and has much better photometric sensitivity. So. But you're right in general.
All right, let's say Somaya again. And last talk of the session is Martin Dominic from St. Andrews University, who's gonna speak about where are the binary source microlensing events.
Now, acknowledging that almost all stars are in binary systems, Schudemann and Botan-Paczynski concluded in 1991 that about 10% of all lensing episodes of the galactic bulge stars will strongly display the binary nature of the lens. And moreover, this could lead to the discovery of extrasolar planetary systems. Rather obviously, not only the lens object causing a gravitational microlensing event can be a binary, but one could also observe a binary source. This was raised and discussed in 1992 by Kim Grease and Wayne Hu, providing a classification of binary source microlensing events, estimating their statistical occurrence and the detectability of their binary nature. Broadly speaking, they are events that are dominated by the gravitational brightening of one source star only, leading to single-peaked and almost symmetric events, and on the other hand, such events that are significantly affected by both stars, some of which lead to two peaks or substantial asymmetries that could be clearly distinguished from microlensing of a single source star. In rare cases, one could see characteristic wiggles because of the orbital motion of the binary, but this is unlikely to happen given that both the angular separation would need to be similar to the angular Einstein radius and the orbital period would need to be similar to the event timescale. In total, Grease and Hu estimated a number of identifiable binary source events comparable to that of binary lens events. However, by 1997, there were 6 reported identifications of binary lens microlensing events in the reviewed literature, but not a single binary source event. This got me posing the question, where are the binary source galactic microlensing events? A key issue is how characteristically identifiable they are. Grease and Hu compared them with an isolated single source star and a single lens object. But if only one of the stars is substantially magnified, the other star contributes a close to constant amount of light, and the binary source light curve is hardly distinguishable from that arising for any other type of blending. That means there should be fewer distinctive binary source events. It's also worth thinking about how much of the blending identified in microlensing event is due to source binarity rather than just crowding. In fact, the binary source magnification is just the sum of the point source magnifications of the individual source stars weighted by the respective luminosities, which means that in particular, one source does not affect the gravitational lensing of the other. In sharp contrast, for binary lens, each of the components affects the lensing near the other, leading in particular to a local tidal field affecting caustics, so that lens binarity leads to stronger and more characteristic distortions of microlensing light curves. Consequently, there's no symmetry with respect to lens and source binarity, as one would be tempted to think at first sight. Well, the reviewer wasn't entirely happy with my little paper, which I actually wrote in a single day, and argued that I should come up with more quantitative results based on elaborate simulations. However, I did not want to dilute a very simple and insightful result with huge amounts of data and lots of details. The outcome of this was that the editor accepted my argument. The paper actually made it into Virginia Trimble's annual review of astronomy and astrophysics, while the reviewer, who was our friend and most respected colleague Chung-Ho Han, carried out the simulation he was interested in himself and published it as a follow-up. In fact, I was quite happy to see respectful scientific debate coming through the review literature, and I think that such isn't practiced enough. So Han and Zhong clearly argued the case that there are to be detectable double-peak binary source events at substantial numbers. Oddly, an early claim of a binary source microlensing event shows the characteristic wiggles of its periodic orbit, which it shows very rarely. So, do we fail to find the common types because those are hard to distinguish from other possible interpretations? Now, both lens binaries and source binaries can produce smooth double-peaked events. And one gets into difficult statistical territory, arguing the case for one of the competing interpretations. Specifically for well-localized planetary perturbations, Scott Gowdy discussed alternative, best-fitting binary source interpretations, typically requiring large flux ratios between 100 and 10,000, which are, however, distinguishable with high cadence, high precision photometry. Now, Scott noted that, as shown, it is likely that binary sources will provide a significant contaminant to a sample of suspected planetary events. Now, this highlights another issue. One of the interpretations looks far more attractive than the other, while selectively the most attractive cases will be attended to and published. Moreover, the difficult or ambiguous one will come out underrepresented. In fact, there's a corrupting incentive of favoring that result that is most likely to end up published in a prestigious journal, and we enter the wider problem that academic publishing is not serving science adequately by mistaking spectacularity and popularity of claimed results for quality. For the OGLE-3 data collected between 2002 and 2008, Jaroszynski and Skovron made some interesting observations with regard to binarity of lenses and sources. Namely, they found that in the majority of cases, the binary lens models give formally better fits as compared to the double source models presented, where formally better translates to fits with lower chi-square. On the other hand, double source models, always producing simpler light curves, look more natural in some cases. Microlensing events can hold surprises in the gaps between photometric data points. Zhong et al. Reviewed the OGLE events, adding in data from follow-up campaigns, and it turns out that a caustic exit was caught as SAO in event OGLE 2006 bulge 238, which seemed to be due to a binary source. Moreover, light curve is pretty flat before, rendering binary source interpretations clearly not viable. There are further events for which the follow-up data hint at a binary lens rather than a binary source interpretation, but as far as I see, the finite size of the sources has not been considered for the binary source models, where it has a substantial effect on the presented binary lens model for one of the events. So we need to assess very carefully what is really ruled out, rather than just claiming a favorite model. This microlensing event, August 2014 BLG 1186, which has a very long time scale of about 300 days, and shows a pronounced asymmetry due to annual parallax rather than binarity. In fact, parallax can even produce multiple peaks in extreme cases, something else to be disentangled. Models with single lens and single source star leave us with a clear and consistent deviation indicating a double peak structure. And this seems reasonably explained by binary lens finite source models. But light curves coming from single lens binary finite source models are almost identical. The major difference being in the exact shape of the second peak, which is insufficiently covered by data for distinguishing these alternatives. One mistake that we initially made was to compare binary lens finite source models with binary point source models, and then disregarded the latter because they did not work that well. In fact, binary source models naturally have two source size parameters, and thereby some additional freedom. The binary lens interpretation looked attractive given its planetary mass ratio indicative of about 45 Earth masses. However, for the binary source models, it was quite surprising to get a ratio between the radii of about 5 and between the luminosities of about 25, which is compatible with two stars of similar color, and moreover with the luminosity gap between subgiants and subdwarfs. The luminosity ratios or the radii and the luminosity ratio are pretty independent parameters. And very easily they could have pointed to completely unreasonable places in the color magnitude. So this is kind of puzzling. A key difference between the binary lens and the binary source models is on orbital motion. The lens separation is of the order of the angular Einstein radius for the binary lens models, leading to orbital periods of the order of years, whereas the two peaks are separated by 1.5 days as compared to an event timescale of 300 days, which is compatible with a binary source separation of about 1/100th of the angular Einstein radius, leading to orbital periods of the order of days or less. While the binary lens models therefore cannot get much better, orbital motion gives the binary source models several further degrees of freedom for reducing remaining residuals, but also challenges their consistency. However, orbital periods could be substantially larger than the estimated minimum, given that we only took a current snapshot of the separation and do not know the radial component. In fact, the source might be even a partially eclipsing binary, but does not have to be. It might be more promisingly identifiable as spectroscopic binary, given the potentially large, relatively large velocities for the close orbit. Event Augur 2016, Bulge 733, also looked like evolving a planet orbiting the source star, orbiting the planet orbiting the lens star, but it shows again how details really matter. In fact, comparing the binary lens and binary source models, there's little difference for the data sets from 3 out of the 5 contributing observatories. A difference in the rising part is spotted by 2, and the wiggles in the tail for the binary lens models are discarded by only 1 data set. It's actually not clear to me whether some orbital motion would remove those wiggles. Finally, I would like to add that astrometric microlensing signatures would provide a quite complementary probe into lens and source binarity. And actually, as pointed out by Chong-Ho Han, as a further follow-up on my little paper from 1998, the blend approximation for binary sources does not hold for astrometric microlensing, and the nature of the blend makes a difference. Thank you.
Question for Martin. Yanis?
Yeah. So in this case, it's odd because you get 2 source stars that are pretty much the same color. So no, it wouldn't help. In this particular case, it would not help. Yeah. So yes, in general, of course, it can give you a further constraint. In this case, we're completely unlucky. We're unlucky in the sense that there's a way to distinguish between these 2 things if you're able to observe something else. But the absence wouldn't prove anything. You really have to detect something that's present rather than something that's absent.
Is there any other question?
Do we know anything about the multiplicity fraction of stars in the bulge? Like, I just don't. Is it just consistent with the disk, or is there any? What's the expectation there? I guess.
I don't know out of my head.
Okay, no worries. I don't know. I don't know either. I haven't really thought about that. I assume it's.
It's full.
Yeah.
Lots of them.
Yeah. Thank you.
I mean, another thought is to what extent can actually the microlensing data give us further insight, in particular for types of binaries that otherwise very difficult to resolve. I actually completely love the resolution power, in particular for binaries that astrometric microlensing has. I think it's more powerful than photometric microlensing, if I'm not entirely mistaken. Ask another one.
But on a related note, Shude, Nate, and I were talking at the break about using spectroscopy to follow up and how that could complement some of these microlensing events. And so I was originally going to say, oh, well, you can look at the color differences and the changes of the spectrum. But Shude was also pointing out that, well, your radial velocities in this case for the binary source could be useful.
Yeah.
Have you done any estimates of these binary source models and what your radial velocity precision would have to be to disentangle or discriminate between binary source and binary lens?
No, I haven't done detailed simulations, but I think it's something extremely worth thinking about.
Scott.
So, just because the colors are the same, that's going to necessitate, for these extreme flux ratios, that's going to mean that one of them's evolved and relatively puffy, and the other one's on the main sequence. So you might be able to see this in the Stark effect of the line widths if you had high enough resolution, right? Because they're going to be different luminosity classes of the stars.
All right, wait. Last question.
minimum orbital period about 0.1 day. And in principle, you can incline the orbit to have larger orbital period, but that would increase the chance to have transit. If you take that into account, what would happen?
I haven't worked it out.